The next speakers are our local hosts, Monika, Schleier-Smith, and John Simon.
Okay, thank you. Yeah, so these last two talks are a little bit different. They're shorter. I think John and I were hoping to just sit back and listen and not even speak, but Dave convinced us to say a little bit about prospects with, at least in my talk, I'll be talking about prospects with for an atom array coupled to a millimeter wave cavity with motivations coming from quantum computation, simulation, and sensing. So this is a project that's actually in collaboration with a couple people you already heard from in this workshop, including Amir Safavineini and Emilio Nani. And these are the folks in my group who are making this work. So our goal is to trap an atom array inside a millimeter wave cavity. What's the kind of motivation behind this? Let me just quickly, for people who don't think every day about cold atoms, just remind you, these are great platforms for a number of directions in quantum science, from precision measurements to computation to many-body simulation, owing in part to the fact that we have kind of the ability to have a high degree of control at the single atom level, a high degree of scalability for making large arrays, and also the ability to have coherent interactions. Currently, the sort of leading way of realizing, for example, a high fidelity gate between these neutral atoms is coupling them to Rydberg states. And so it's a very powerful toolbox. Now, one potential limitation is that sort of in the simplest case, the interactions between the atoms are local. They're kind of on the few micron scale. And there are reasons why one might want to go beyond that, which are kind of the motivation for the project I'll talk about. That includes engineering sort of scalable entangled states as resources, for example, for quantum metrology. So if one can have many atoms with collective interactions over long distances, or long on the scale of an atomic experiment. So many atoms that can talk to each other collectively, that can give a way of sort of efficiently generating all-to-all entanglement in the form of, for example, squeezing for quantum sensing. But perhaps pushing this towards fundamental limits requires some new technologies. If one has non-local connectivity, that can be a resource for more efficient error-correcting codes, or also for thinking about sort of how does one design quantum algorithms in the most hardware-efficient way. And in the context of quantum simulation, going beyond local connectivity offers prospects, for example, stabilizing exotic phases of matter like spin liquids, or even sort of simulating models from fields beyond condensed matter, so like exotic interactions of interest for studying models of quantum gravity. So these are all kind of broad motivations in our group for being interested in realizing a system where one has non-local interactions in these cold atom systems. And broadly speaking, there are kind of two approaches you might take to this. One powerful approach is actually saying, well, let me stick with these local Rydberg interactions that are so far, again, kind of the most coherent gates we have. And then let's move the atoms around in order to have some effective longer range connectivity. So one approach is shuttling atoms around, or the other idea is keep the atoms fixed, but let them talk to each other via some delocalized mode of light. And that's actually closely analogous to also what's done in trapped ion systems, where one has, in this case, ions that are linked by collective motional modes. So here the bosonic mode is a mode of motion. For us, the bosonic mode is a mode of light, but that sort of mutual coupling of many atoms to a single mode is then another way of having beyond local connectivity. And in this case, one sort of very naturally actually gets global connectivity. In the simplest case, every atom will talk to every other. And some of the work that's been going on in my group is also asking how can one go beyond kind of all-to-all connectivity to really having sort of programmable non-local connectivity for cold atoms. I could give a whole other talk that I don't have time for today on how we sort of realize programmable non-local connectivity in the setting of an optical cavity. So we do experiments where we have an array of atom clouds that can talk to each other over sort of the millimeter scale distance over which the single mode of light is focused. And we've been exploring ways of having kind of entanglement with programmable, a programmable graph of entanglement, of having programmable interactions that give new tools for quantum simulation, and applying this system on the one hand for applications, let's say in multi-parameter sensing, benefiting from this programmable entanglement, or having sort of new probes in quantum simulators, whereby being able to couple to non-local degrees of freedom, that can be a new way of programming a topological state of matter. So these are some of the things we're doing in the optical domain. And broadly speaking, we kind of benefit from, I would say, kind of two well-established tools. One is this notion that coupling many atoms to a single mode of light is a nice way of efficiently generating collective entanglement. And then the other one is sort of, I would say, a fairly recent development is sort of combining this type of setup where one has many atoms talking to a single mode of light with these tools of local control and detection imaging single atoms that, or in our case, single atom clouds, but in other experiments, single atoms. And that's sort of a nice toolbox for having programmable non-local connectivity. So the key building block for this toolbox is basically, in the simplest case, if you imagine having two-level atoms and you want them to talk to each other via a cavity, one thing you can imagine doing is having some spin exchange that's mediated by a photon. So some process where you can flip a spin, put a photon in the cavity, another atom absorbs that photon. That would give you kind of like an eye swap type of a gate between these two atoms. I said we don't work with two atoms in the experiments I showed so far. We work actually with clouds of many atoms. And one of the reasons for that is that actually having very coherent interactions, if I actually just want this coherent spin exchange between two atoms mediated by a photon, I actually need to be very deep in the strong atom light coupling regime. So that means that actually most of what's been done in this space of sort of photon mediated interactions between cold atoms has either relied on this approach of having ensembles with some collective enhancement, and that can actually be a sensible thing to do, particularly if you anyway want many atoms because you're doing a precision measurement, right? So collective enhancement is one way to go. Or there's been some work on heralded gates between two atoms, again, sort of benefiting then from detection from heralding to be able to have a reasonable gate fidelity. So just to say a little bit more about, what do I mean when I say one wants to be deep in the regime of strong atom light coupling? Aziza, and perhaps already others before her, mentioned this sort of figure of merit, right, that we care about in these Cavity-QED experiments is the cooperativity. So the square of the vacuum Rabi frequency divided by these characteristic decay rates of the cavity field and the atom. And just to kind of, give a sense of how does this play into what you can do with the cavity, if I want to do a 2-qubit gate, the error in that gate is going to scale as 1 over the square root of the cooperativity. So actually, like, if I want to kind of push down these gate errors, the square root scaling isn't great, right? I really need to increase my cooperativity a lot. In sort of the context of many atoms, one can do things like make squeeze states of the atoms, where the squeezing parameter depends on the collective cooperativity. It's enhanced by n. And so that's why that's sort of a regime where there's more been done in the sense of sort of, generating collective entangled states. So, that works for Gaussian states, but if you want to access non-Gaussian states, you do want to be in the regime of single atom strong coupling, and the collective enhancement isn't enough. What parameters are realized, and again, Aziza already set the stage quite well for this. In the optical domain, there's different approaches ranging from macroscopic Fabry-Perot cavities to nanophotonic devices. But typically, this cooperativity, essentially in all systems to date, has been limited to a couple hundred at best. And so, it's much larger than 1, but when you say that your gate fidelity, if you want to do a gate, the error goes as 1 over the square root of this, and there are numerical factors that always go the wrong way. It turns out that this is maybe it would be nice to do even better. And the millimeter wave regime is great for doing even better. This is picture of, well, I guess it's actually half of the celebrated Hirosh group cavity. This is a superconducting niobium film used to create one of two mirrors in a Fabry-Perot cavity. That cavity has a finesse of about 100 million, sorry, a cooperativity of about 100 million, right? So this is orders of magnitude higher than what's possible in the best optical cavities. And so this is a regime that sounds attractive, and we started to ask, also inspired by the nice experiments that Aziza mentioned together with John and Dave. We started to ask, can we kind of combine this millimeter wave cavity technology with the atom array technology that I showed on the first slide? So that's our goal. Right, so the idea would be have this sort of millimeter wave Fabry-Perot cavity, Fabry-Perot, so that there's it's a reasonably open geometry with some optical access. And we'd love to be able to trap an atom array inside. And roughly speaking, we've drawn inspiration from this seminal work in the Hirosh group, where the basic design is a niobium film on copper for forming this superconducting cavity. And just to sort of, so that you're not disappointed at the end of the talk, I'll say we have not yet trapped an atom array inside a cavity. We have an atom array, we have a cavity, and they're not yet in the same apparatus. But thanks to our collaboration with Amelia, we've been able to start testing the design of a cavity that's appropriate for these science goals. And so what I want to say a little bit about in the remaining time is sort of, first of all, just like give a bit more intuition for like, why can one do orders of magnitude better in the millimeter wave domain than in the optical? That comes from thinking geometrically about the cooperativity. Just as an aside, why is millimeter wave better than optical? There's an argument just in terms of the strength of the coupling, but also having a long wavelength is great for having space to have a large two-dimensional atom array, right? So that's also kind of a nice geometric feature of the millimeter wave regime. And then I'll also comment on, what are the atomic transitions that couple to such a cavity? And is this design with high finesse, is this in fact compatible with the type of optical access you need for tweezer trapping and imaging? And that, I think, is the part that maybe hasn't been entirely clear from past experiments. So Aziza built this very cool crossed optical and millimeter wave cavity system, but in a way that one doesn't have sort of a large solid angle for imaging the atoms inside. And these seminal experiments in the Hirosh group used just sort of a beam of single atoms passing through a cavity with a relatively closed geometry. Okay, so let's start with this first question. Why is the millimeter wave regime so great? So I found it really helpful to sort of think through, for, I assume, a Fabry-Perot cavity, what is going to matter actually for this cooperativity? I can write it as g squared over kappa gamma, but another way I can write it is actually just the finesse, which essentially tells me how many round trips the light makes, times the solid angle that the mode subtends in the far field. And that solid angle will be bigger, essentially the shorter the Rayleigh range is of this Gaussian mode compared to the wavelength of the light. So the solid angle can actually just be expressed as the wavelength divided by the Rayleigh range. Okay, so clearly I want a high finesse. And then one other thing that I find useful to think about is, roughly speaking, typically if one wants a stable geometry, the cavity length is going to be something on the order of the Rayleigh range. And you can push that a bit. You can go further towards concentric and make the cavity longer or closer to planar. But roughly, as a starting point, I can sort of say, well, for something near confocal, that's a stable geometry, what matters is the finesse, essentially divided by just the number of wavelengths in the cavity, right? Essentially, like, it would be nice if the cavity length is not too many wavelengths, just sort of order wavelength, a few wavelengths perhaps. And then what also is good, of course, is high finesse, but that's also easier to achieve. Both of these are actually easier to achieve if the wavelength is long, right? If the wavelength is long, I can sort of fabricate mirrors that are very smooth on this relative to the scale of the wavelength. Whereas if I have kind of, let's say centimeter scale mirrors, but my wavelength is a micron, this lambda over L factor immediately penalizes me as it would in the optical domain. Okay, so long wavelengths are good. long wavelengths. So we'll talk about millimeter waves. The transitions that they'll couple to are transitions between Rydberg states. So that's kind of the basic game is going to be couple Rydberg atoms to a millimeter wave cavity. And one other sort of comment to make when we think about what atomic states we're going to use, this argument I gave here where it's a purely geometric argument, the intuition is kind of, right, an atom, I want it to decay into this solid angle that's subtended by the cavity. That argument assumes that kind of the transition that couples to the cavity is actually the only transition on which the atom can decay. So that's not generically going to be always true. You'd like sort of a two-level atom or a cycling transition, or in the case of Rydberg atoms, the kind of ideal level scheme would be using what are called circular Rydberg states. So these are states with high, so Rydberg means high principal quantum number, but circular essentially means for a given n, if I put myself in the state with the largest possible angular momentum, so L is equal to n-1, and the z projection of the angular momentum is maximal, so it's kind of a stretched state. Then selection rules will actually tell me there's only one decay channel for these circular states, and so that's going to give me that sort of maximal cooperativity that's determined just by the geometric parameters. And that means these states can be very long-lived, at least if one goes to cryogenic temperature, so that black body radiation isn't a factor. So here's sort of like a typical state we might want to work with if we want to transition around 75 gigahertz. The lifetime will be more than 10 milliseconds as long as we get down to temperatures on the scale of a Kelvin. And in fact, this number, which we sort of started out with as a target of around 75 gigahertz for the transition between circular states, it's a regime where one can have, so in addition to the long Rydberg state lifetime, one can have low thermal photon occupation in the cavity at this kind of same temperature I considered here of about the Kelvin. And one can also expect at a temperature of around a Kelvin that if the only thing limiting you were sort of the BCS resistivity of this superconducting film, that would limit the finesse to something on the scale of 10 to the 11. So that's sort of, in practice, more likely than to be limited actually just by the roughness of the mirrors. So this is kind of the regime that we're targeting. Okay, so I said a bit about, why millimeter wave, which atomic transitions would one want? And then what I haven't yet addressed is this idea of like this high finesse of the superconducting Fabry-Perot, is it actually compatible with having the optical access one needs to trap atoms in tweezers inside? So you can think through this again. There's, I said the cooperativity basically depends on having a large solid angle subtended by the mode. So you also kind of, and also the finesse will be highest if the solid angle kind of the mirrors is large, but I also want a decent aperture open from the side. And typically for sort of single atom tweezers, one wants kind of a numerical aperture of about a half transversely. So we can kind of plot the landscape of if I can choose the length of my cavity, I'll put it here in units of the Rayleigh range, that's one axis. And if I can choose the Rayleigh range in units of the wavelength, so that's sort of deciding on the mode geometry, how well can I do in terms of getting both high finesse and good optical access? So the colors here are just showing essentially the numerical aperture that one expects. If I sort of choose the mirror size so that clipping losses will allow a finesse as high as 10 to the 10. So and this is in some Gaussian approximation of the mode and how much it will clip. And so as I sort of vary the length of the cavity versus the Rayleigh range, the white dashed line is the confocal limit. One sees that, if I go too planar, not too surprisingly, right, if I put the mirrors very close together, I won't have enough optical access. But somehow there's a point of diminishing returns as I go beyond confocal. So somewhere around confocal is a reasonable place to put the mirrors, the length being roughly, confocal would be twice the Rayleigh range. And then vertically basically is saying, how do I choose the divergence of my mode? How short is the Rayleigh range in units of wavelengths? And here I can get that sort of target numerical aperture of about a half for some choice of the Rayleigh range being, let's say, six wavelengths or so. So there is a reasonable place to work where just the mirror size won't limit the finesse until it gets to 10 to the 10, and the numerical aperture from the side will be fine for trapping and imaging single atoms. Okay, so that's kind of our informs the design. And so, we said, let's go somewhere near confocal. We don't want to be where the modes are degenerate, but there's no point in going much longer than that. So we built a near confocal cavity, and thanks to the collaboration with Emilio, put this in his fridge and did some measurements of the finesse of different modes. Tony Zhang, again, was leading this work, and I think quite heroically figured out how to take a spectrum like this and interpret it and understand what all these modes are. Okay, and one thing that was initially disappointing is we looked at the finesse, and it was somewhere in the 10 to the 4 to 10 to the 5 range. And what we realized, one thing that was limiting this is that actually, even though naively in sort of a paraxial limit, one would think that the cavity is far enough from confocal that the modes are well separated. The reality, if one accounts for kind of non-paraxial effects, is that there's some mixing between the TEM00 mode, that's the one we want, and higher order modes. And that sort of shows up, for example, in some avoided crossing here in the spectrum of the modes of this cavity. And at that avoided crossing, there's a big dip in finesse. Okay, so one has to be a little bit careful. This was too close to confocal, so we tested out the cavity at a couple of other lengths, going just slightly further away, just a few % further away in terms of the ratio of the length to the mirror radius of curvature. And then we're able to sort of measure finesse versus as a function of mode frequency and see that at least for kind of higher frequency modes above 90 gigahertz, we're able so far to get a finesse that's around up to 60 million. And this is also showing now the finesse versus temperature for, I guess, the mode in the box here. And so as long as one is below around a Kelvin or around 1 Kelvin, the finesse here is limited by, well, something other than the BCS resistance in the superconductor. So it's plateauing. And if we want to know what limits it, there's a couple things you might suspect. One is the surface roughness of the mirrors, but that actually would be this dashed line here. That would actually limit these modes to something above 10 to the 8 in finesse. But it turns out this measurement was actually not done at zero field. So the dominant limitation, we think, is actually some magnetic flux trapping in the superconductor that will be improved when we do this at zero field. At lower frequencies, the different lengths still show a difference in finesse, indicating some residual effects of kind of mode mixing. But at high frequencies, that so far is no longer a limitation. So I think this kind of shows there's some room to even push this higher, but we're actually quite happy already with these sort of parameters that we've already directly measured for this cavity. In terms of a cooperativity, this would give a cooperativity of 3 million for the circular Rydberg state that's at this frequency of around 95 gigahertz or so. So that would be a fun regime already to start trapping atoms and exploring a range of different directions, from asking, can we use now this millimeter wave cavity to mediate non-local gates? And we'll start by trying to do a gate between 2 atoms, but sort of longer term, there's space in there that one could have, an array of atoms that's my data qubits and another array that are perhaps ancilla qubits that can allow you to manipulate or detect some non-local operators in the data array. We're also interested in quantum state engineering, using the atoms to manipulate the millimeter wave field or vice versa. And this could be a nice platform for accessing non-Gaussian states. Sort of drawing inspiration from what's been done in, I think, drawing inspiration, for example, from some of the beautiful work that can be done in superconducting qubits coupled to cavities. So I think a nice thing here is, again, the scalability to many atoms. One can ask, can one access kind of scalable resources for Heisenberg limited sensing? And then I think another important question is, I've been focusing on the fact that this cavity is a way of having some non-local connectivity, but these Rydberg states, if you put them close together, the atoms, they will also have local interactions. And so there's, I think, a fun question about how does one optimally combine the ingredients of kind of local interactions or gates with this kind of cavity-mediated global connectivity. And lastly, that interplay of local interactions and global interactions, I think, is a rich playground for studying quantum many-body physics. And there are some concrete theoretical proposals of how this interplay can give rise to anything ranging from spin-liquid phases in systems that otherwise would not be frustrated to fast scrambling, so sort of very rapidly generating complex entanglement. So that's concrete proposals, but I think also the broader question is what are the new surprising emergent phenomena one might see from this interplay? Okay, so with that, I'll just thank the folks who are pushing this project forward. Everybody here in green is on this millimeter wave cavity team, and particularly Tony Zhang is the lead, who's on characterizing the millimeter wave cavity. And I'll also thank one more time our collaborators. Yeah, Caesar.
I have a question about these cavity-mediated gates with the fidelity of 1/√C. So there are some newish proposals with like the counterfactual one. I think Mark Safman, like a couple of weeks ago, also had like new cavity-mediated protocol that fidelity scales a bit better. I think most of the time you have to sacrifice in efficiency, like heralding then starts scaling with 1/√C.
So I should emphasize those. That was for a deterministic gate, right? And so that was why I mentioned early on sort of what's been done. Everything that's been done so far in terms of like 2-qubit gates in cavities benefited at least in some way from heralding. In some cases, they're like the Rempe group did a nice experiment with a gate that it was deterministic, or like the protocol in principle is deterministic, but to actually kind of get I forget what the fidelity was, but maybe order 90% fidelity, they relied on heralding in addition to that.
So I guess your goal is to kind of not having to like reduce rates for
what you can do in terms of just I would say deterministic entanglement lets you do things beyond what you can do with heralded, right? Particularly if I want to do a sequence of gates, if I have to herald, right, the probability that all of those will work goes down. So I think for some applications, like for long distance entanglement, the optical regime is good if you want to really bridge long distances and think about quantum networking applications. But if I want to be able to do more complex quantum circuits, then I want to be able to do things deterministically. Yeah.
Due to the limit of time, I think this is the last question.
Thank you. So is there any intuition behind the statement that the fidelity of 2-qubit gates scales as 1/, the cooperativity of 1/,
yeah, I mean, I think roughly, I think the reason this is fairly fundamental is somehow like I need to put a photon into the cavity, and then I need another atom to absorb that photon again. And the cooperativity is basically, 1/, the cooperativity would tell me something about the error of just kind of putting a photon into the cavity versus losing it. And so like if I want to do something, and so there are some schemes based on detection actually, where like if my goal is just to actually have a photon emitted by an atom into the cavity and detect it, then typically the cooperativity without the square root might be the figure of merit. But if what I want to do is coherently exchange information where I need to, essentially have the photon be emitted into the cavity and absorbed by another atom, you kind of take that hit that you go down to the square root as what matters. So I don't know if that at least hand-wavingly gives a feel for it.
Thank you.
Yeah.